All right. So anyway, I was going to talk a little bit about each part of the project, if that makes sense. How many people have made some reasonable progress on things? Some of you? A few of you? Okay. So for those of you, it may be, depending on what we do, it may or may not be useful. And then I'm also open to other kind of questions or things that'd be worth talking about. So why don't you think about that while I'm doing a little bit of intro, and then we'll go from there. Okay, so this is the Linux part of the project, which is you're building a little distributed file system, which should be fun. And actually, though it's probably the most code you'll write this semester, it's actually, I think, fairly straightforward if you just pay attention to the details. So we'll find out if that's true. You should be looking at this, what we looked at in virtual class last time, which is this UDP messaging code. How many people have run this code? A few of you? Okay. So anyway, let's just go over it again real quick, and then I'm going to add a little bit of functionality to it. In particular, we're going to look a little bit at how to do something like a timeout, and therefore maybe a retry. And we'll use a special system call called select to do that. Has anybody used select before here? Okay, so at least that'll be new. And then maybe we'll talk about a few other things, and then we'll switch to the other side of the project as well. So this code that we gave you is just a real simple library that I think I wrote actually at some point. I don't even remember. And it just basically does UDP communication. As you might know, UDP is an unreliable protocol. So that means it's a what's called a datagram protocol. So basically, you just send packets from one machine and port number to another machine and its port number. Port numbers are just used to identify different communication activities that are happening on a particular machine at the same time. So if you just send a message to a machine, you don't really know like which, say, process you're talking to or anything like that. So you need some other way of identifying individual communications, and the port number is used for that. So that means the server side of this code, and there's client and server, will set up and start at a well-known port number. Here I'm using 10,000. In your program it'll be, I think it's specified on the command line. Yes, that you have to say what port number, and then you just use that. And then the server just basically does a basic loop here, which receives a message by calling UDP read, and then in this case just replies immediately by calling UDP write to this socket descriptor that's handed to it. So actually UDP communication, except for just a few details, is pretty straightforward. And you can look at the implementation of that if you want to see some of those details, but there's really not that much going on inside this little library. So does that basically make sense? Your server, of course, is going to look something like this, right? It's going to read a message. It's going to figure out what message it is, like, oh, is this a lookup request or a read request or whatever, and then it's going to do that work, and then it's going to reply. So this basic loop of your server is going to be very similar to this. It's just more of it. So one high-level piece of advice I would give on this part of the code, you can kind of do the networking part separately from the local file system part. Like you can build the server, not doing any communication stuff, just build the server, build those routines, right? Like lookup, whatever, whatever, whatever. Build those routines, make them work, test them by including like a main in the server that just calls those routines in some way. And then when you're ready for the communication piece, which you can imagine even somebody else could be developing, you can kind of plug it in and connect receiving a message and then calling one of those functions and then sending a reply back to it later. So it's really, you could view those two as very separate things that you could do, and I would certainly develop them separately and maybe test them separately. Okay, so just a couple details here. You read or write a socket descriptor. You have the socket address, which on the receiver side is basically just going to be filled in with who sent the message. Here I'm passing an arbitrary buffer, and maybe in a minute, if it's interesting, we'll just look at how to pass a structure. It's not hard. I hinted at it in the last video. And then let's look at the client side. The client side is a little bit more complicated because you fill in the socket address here. It's on this machine, which is Mumble 19, and the port number. So this is basically saying the messages that I send from here, where are they going to go? And then I write to this socket descriptor specifying that address, again a message and the size of that message, and then I'm waiting for a reply here. So any questions about that code? Does that code basically make sense? Okay, and so what we're going to look at, oh, and so one thing that you might realize is that this filling in of the socket address, whatever, that's something you're probably going to do once in your library, right? And then you're just going to keep that socket address structure, address here, around so as to be able to communicate with the server, right? So that's something you would just do probably once. Well, you could do it on every communication, but why would you do that? Okay, so the problem we're going to deal with is, well, you notice here we send a message by calling write, and then we wait for a response by calling read. Let's take a peek at that for a second. So you run server, for example, and already in use. All right, that's good. Was that my own fault? No, maybe. You know what? I'll just change it. So that's funny. I should have made this more flexible, but I didn't. Okay, so server's up and running. You can see that you can't have multiple people listening, multiple processes listening to the same port number at the same time there, so it'll say it's in use already, and you may run into that if you have bugs in yours. And then of course we can run the client, and it should, the client says I sent a message, the server says I received it, and then the client goes ahead and gets the reply back. So that's not too exciting. Let's go ahead and kill the server. So what happens if I just run the client and there's no server? You don't receive a reply, right? It just hangs. And the reason, that's not too surprising perhaps, but the reason for that is, well, there's nothing. We send a message. We don't know if anybody ever really pays attention to that message at all. We just sent it, and then we're waiting for a reply. That reply never comes, and read is what you would call a blocking call. Once you call read, it's only going to return if there's some kind of error, something very strange happened, like you passed in bad arguments or something like that, or you get the data. So read is a blocking call, so we don't want to call it unless we really know something is available. And it turns out there's a way, so this is a pretty common problem, and so because of that, people long ago developed a way to check before, like calling read. You want to be able to check, is there something there? And that routine is called select. So we're just going to look at that briefly today. You can do a man on that if you want on Linux, and we'll see a few things about it here. There's actually a select routine that we're going to be interested in. And then there's a few routines that we'll use that are basically auxiliary routines that help out with that, and so we'll talk about those in a second. And it's pretty straightforward. The select man page is useful, and by the way, also I believe they say down here somewhere on this long man page, which of course you should read because you're using the interface. They also say there's this useful select_tutorial man page, and I actually found this page to be slightly more useful. So you can look at that too, and it's obviously it's similar, but it has a few different explanations of things. And I think it's actually kind of a better set of explanations. Okay, so let's include this thing if I haven't done that already. Let's make, well, let's just do it right in here. That's fine. Sorry. Yeah, it's already in there, so no problem. So basically what we want to do is, well, what does this code do is it says I'm going to write this message. You know, I do this error code checking, but we don't really, let's just ignore that for now to make the code a little simpler. And then we say we're going to do a reply. And what we're going to do here is we're going to try to use select in some way to check if there's actually something there to read. And so let's look a little bit at the man page to make some sense of what the different arguments are. Okay, so what basically we're going to pass to, there's a few things to look at here, and a number of them are important to you. The first is, let's ignore this for a second, the kind of number of file descriptors or socket descriptors we're interested in. Let's ignore that. The next three arguments are basically this type fd_set. And they're basically going to tell select, are we interested in sockets that we can read from, which is going to be the case here, right? We want to tell, can we read from this socket? So we're going to be pretty interested in this argument. Also, you can check if you're able to write to something. Sometimes writes can block. For example, if there's no buffer space available, a write could block too. We're not interested in that in this project, but you could imagine that being useful. And then this one relates to there being some exceptional conditions on some of these sockets that you're communicating on. So what we're going to basically do here is say, we may have a number of socket descriptors that we're interested in reading from. Here is just one, but you could imagine in a more complicated server it's many. So what is that set that we're interested in reading from? And then select, we're going to use select to tell us that yes, something is there to read or not. Does that make sense? Basic idea? Question? Are you recording this? I am recording it. Yes. Good question though. You're like, okay, now I can. You better not sleep now. So in any case, that's what the basic idea behind these FD sets are. You're basically telling select, oh, I'm interested in maybe reading from these or writing to these, or so if there's some exceptional case going on here. So please tell me about it before I go and call, say, read, and then get stuck blocking, because I want to know something's available. The number of FDs over here is going to turn out to be a way of like restricting how many or what's the highest FD I should pay attention to inside of select. And so we just have to make sure that's one greater than the number that we're using, or the number of the socket descriptor that we're using. And then pretty interesting for us as well is this timeout. The timeout is going to basically say to select, tell me when, say, something's available for reading, or if, say, some number of seconds have gone by, then just return with a different error code. And that's the way we can basically, therefore, know if we can wait for something to be there, like a response, or we can basically just have select return after a period of time, and then we can do something else, like maybe send the message again. Make sense? Questions about that? Okay, so let's fill it in a little bit. Is this too much code to be giving you? I don't know, but it's late in the semester. We're all trying to help each other get through it. How are you helping me get through it? Actually, I have no idea, but I'm trying to help you get through it. So let's look at this a little bit. You are helping me get through everything by just being positive and cheery about things, and studying a lot for the final exam. That'll help me, because then you'll all be perfect, and I will just grade it by looking at it, and I will say, this is perfect. I don't need to grade it. So, okay, great. Anyway, so the first thing we have to do is create one of these FD sets in order to, that's okay. It's getting violent down in the front row, if you can't see from the back. People are throwing things. You really missed a very interesting discussion, anyone who's listening online. And in any case, what we're doing is we're trying to figure out how to make one of these FD sets so that we can select which socket descriptors we're interested in. It turns out that's pretty easy. Well, let's just create one. We can call it R. Just create it like a variable. And then we have to use these routines here to basically set this up. So the first thing we have to do is we have to zero out this set. So let's go ahead and do that. And these are just the routines here, right? I'm just using these for reference. So we'll go ahead and do that. And then what we're going to do is just set one of them. We're basically saying we're interested in a particular descriptor in this set. So the way we do that is just say FD set. And then the descriptor we're interested in is, of course, this socket descriptor that we created right here. So, and then we're going to be using down here to read from, right? So we just go ahead and do that. And at that point, we basically have this set of descriptors described in the way that we're interested in, which is we're just interested really is there going to be something to read in this one socket descriptor. So we're going to replace this argument here then with the address of R. Okay, make sense? Now the next two, the write and exception FDs, we're not interested in, so we'll just make those null. And let's not do a timeout at first. And then the last thing we have to do is do this argument correctly. Let me get rid of that. This first argument, and it's easy to get that wrong, so let's go ahead and look at the man page of the tutorial man page. I think described this better when I was looking at it earlier. And this says this is an integer one more than the maximum of any file descriptor in any of the sets. Why is it that way? I don't know. That's just what they decided. It's easy that way, so that's what they do. So it's one more than the max file descriptor, and we know SD is our file descriptor, so SD plus 1 would be one more than that. So we'll just go ahead and do that. We have a return code here that we'll use, and so what we'll do here is we'll just print out that return code. Okay, any questions about that? Make sense? Now, I guess it's not too interesting, but let's go ahead and make it and see if it works. We'll run the server again, so still not that interesting. We'll run the client. You can see here we're about to call read, select, the server receives a message, replies, select, then returns. It returns, hey, something's available, and then the client goes ahead and reads it. Now this doesn't solve our problem, because if there's no server still, the client will still, it'll get stuck. In this case, it'll get stuck in select. Right? Select waiting for something to return. So that's what we're going to fix next. So let's do that. Where are we going to do that? Let's look at the man page again real quick. Well, we can see we just have a struct time val with a timeout. Okay, time val is a pretty standard structure that's used in these kinds of situations. So let's declare one. Let's call it T. And if I remember correctly, that has two fields, seconds and, say, microseconds. Probably don't care about any, it's the sum of those. So it's not like one or the other. You fill in both. So this would wait for 10 seconds. This would wait for 10 seconds and 1 microsecond, etc. And what we're going to do here is we're going to just simply pass that structure in and basically tell select, yes, either tell us when there's something available for reading, or tell us that something happened and we timed out. And let's see exactly what this is going to, we have to, of course, check what select returns in that case. Blah, blah, blah. There's a lot to read on this page. I'm not going to read that page again. Too much to read. So here, return value, always a useful section of the man page to look at. I'm sure you're all experts at this now. On success, return the number of file descriptors contained in the 3 that return, which may be 0 whatever. If there's a timeout, or -1 on an error. So it says this may be 0 on a timeout. Otherwise, it's going to be the number of file descriptors that have something interesting. So we saw last time there was a 1 returned. But basically what it's telling us is if the return code is greater than 0, that we actually should go ahead and read. Otherwise, let's go ahead and do something like print, client timed out. And of course, you could retry it then, or basically just go in a loop and send the message or something like that. But here we're not going to do that. We're just going to time out and exit. Okay, so does that make sense? Okay, so let's, I guess I should stop the server from running. And then let's see what happens when we build this. That's all good. And then we're going to run the client with no server available. So in this case, what we're hoping will happen is that we'll go into select, we'll wait for a while, and then it'll return with an error, or not an error, but saying nothing's available, so you should do something else. This is the point where I wonder why I made it 10 seconds. I guess it really makes you believe it worked. And there you can see it timed out. So that's that piece there. And then, of course, we could run the server and make sure it's really working, because we don't want it to time out in that case, too. And hopefully what happens there is select returns 1. Yes, there's a file descriptor somewhere in there that's ready. And therefore, go ahead and do the read. And you can imagine there's, remember, this is a more sophisticated interface than what we're using here, right? You can give many file descriptors, or socket descriptors really is what they're talking about, to check. And you can imagine why, therefore, some of these other macros might be useful. Because what you need to figure out after the routine returns is, well, which socket descriptor can I read? Here we know it has to be this one, but if we had multiple ones, we'd have to do a little bit more logic to figure that out. if that makes sense. Oops, am I running anything here? Yes. So that is that piece there. Any questions about that? Yeah.
Should we use it just for the user period, or should we use it also for user write?
I don't think you need to use it for write, because basically, if that blocks, it just means that there's some buffers are full, and presumably they're draining in the background. So you're not going to do anything different there. So this is very much a structure like this, where you write on the client. Like basically, this is the client-side code that I'm giving you some details on, right? Which is saying, when you're sending a message to the server that you're building, just do this. Send the message by writing, then set a timeout, use select, see if you get a reply. If you don't, then just try the whole thing again. And you can imagine that's then pretty robust, right? You can start the client even ahead of the server starting, and it just kind of keeps sending messages to the server, and then finally the server, you can start it, and then it will connect and go from there. Okay, any other questions about that? Good question. Okay, one more thing I'll just do very quickly. We don't have to send, this is just, the way to think about this, even though like write is kind of expecting looks like an array of characters, it's really just a bunch of bytes that you're sending of some size. So you can put anything that you want in there. We could, for example, just define a struct message or something like that, and always send a particular message over that's just a bunch of bytes. So we could have like this is message type, and we could have some data in there, like a block that we're reading or writing, or other stuff. You can just define a message like that, and in fact, you should think about, you should probably have just one message type which can handle all the arguments that you need to pass from the client to the server and back from the server to the client, and have everything you need in there, and then just always send it. That's kind of the simple way to do this. So define whatever that message is, put it in some sort of shared .h file, like message.h, include that in the client library and the server, and then go ahead and, instead of sending a buffer here, you'll just send a message which is of that type, and you'll say it's size of whatever, struct message. And of course this might require you to, this is the reading side, but you might have to cast it or something like that. Casting isn't doing anything other than making the compiler happy, so you should always make the compiler happy. But here we're just saying, so these are the bytes, this is the length, send them over there, and the other side will figure out what to do with them, and then we can see how that works. In fact, I guess we'll just go ahead and do it so you'll believe me. Let's make a struct message here. I call it m. M.type equals whatever, let's say equals 100. We don't need to put a message in there anymore. We'll go ahead and say something like this. Okay, so now we're sending this message. We filled in one of the fields. You can imagine filling in the others. That's not too hard to imagine. Over here, we're receiving a message of that same exact type, and that's perfectly reasonable here. And let's make sure the server, we can do something similar over here. Now, like I said, what you really want to do is you want to have a shared H file that has this definition of messages in it. But I'm just going to copy it because I'm being lazy, and why not? And so then here, instead of this buffer again, we would just do struct message m and receive it into the same place, and then we'll just print out that we got those correct values, if that makes sense. And that's that, and we don't need a reply here, so we'll just, we'll say m dot type equals 11 or something like that. What did we say was another side? 100. Okay, so let's make it 101. So anyway, oops. That's kind of the idea there, and let's make the, sorry. Let's print out that we got the message, got message, %d, whatever, m dot type. Am I missing something? I print out something over here. No, probably here. So we'll read that the message is not buffer, but let's read the type field. That looks close enough. UDP write server.c. Yes, forgot one cast over here. Okay, so let's see if this works. Got message 100, that was the type we sent over, and over here we got the reply. So we're just sending a structure over, right? And we don't have to, if you were doing this in a more generic context where you had different types of machines, maybe with different endianness, you'd have to worry about that because you'd want to then make sure that you can't just send a struct to another machine and hope that the bytes end up in the right order. But here we know it's all in the same type of machine, so we don't have to worry about that. So we can just send a struct, and when those bytes end up over on the other side, it's just going to be in the exact order as expected, so no problem. Okay, so you'll be doing that, and you'll have to figure out a generic message format that works for all the protocol messages. It's not that hard to figure that out. There's a very limited protocol there, so just figure that out, and then always send that message. And then on the other side, you're just going to basically, you can imagine what that server loop's going to look like. It's going to look at the type or whatever and say, oh, is this a lookup? Call lookup, and then take the response from lookup, put it in the message reply, and send that message back. Is this a read? Yes, it's a read. Okay, extract the arguments, call read. Then get the results of that, whatever. So you can imagine that you can make a stub library that calls those routines, look up whatever, read whatever, and just make sure all the arguments get over to the other side and a dummy response returns, and that the retry stuff works. That's like the communications portion. And then you have to plug those routines on the server side into the working file server, log structured file system piece. And that's the file systems piece. And that's probably a little more work. Okay, any other questions about that? Yeah.
Can you go over how to build a library?
I'm going to say no. but if you have trouble with it, the thing you can do there is it's almost identical to, so I'll go over it verbally instead of just doing it. But verbally, it's almost identical to the library you built before when you did malloc. The only thing you can do is you can, throw udp.o in there too, as well as, your libmfs.o or whatever you're calling it. So you're just going to take two object things, throw them together, and make it, all the other instructions are exactly the same. And I know sometimes people struggle with the makefile piece. One thing that I would suggest there is spend some time reading about make. It's actually not that complicated. But if you're really struggling, like I can't build it, but I know what the build should do, then just write a 3-line script that just does that thing first. And you can worry about getting the makefile to do it correctly later. That's not the important piece. Don't get hung up on things like my makefile is confusing. You can ask us about that, but in the meanwhile, just build the code directly by calling GCC in the right way. Okay, so I was going to skip over to the XV6 part. Are people have other questions about this part? Yeah.
When we load the file system image,
Yeah.
am I misunderstanding? Like, is it involved, like, can you call open, but then open if you have a file that doesn't exist?
Okay. Yeah, I understand what your question is, I think. So there's something that's a little bit confusing here, which is a little bit the nature of the project. You're building a log structured file system, but you're not doing it on a raw block device, which is what you would normally be doing when you're building a file system. In fact, when we look at the XV6 file system, we're reading and writing blocks, right? That's the interface we have. We can read blocks from the IDE disk that's attached to your virtual machine, that is your emulated disk. And of course, most file systems would be built that way. You're reading and writing blocks, and that's the only interface you have, and you're turning that into something that looks like a file system: open, read, write, close, whatever. Here we have it's a little bit different in that what you're basically building that kind of file system, but on top of a file. So that's already, it's a little bit strange. But you just have one big file that you're going to open and or create. That is going to, we're pretending that's a disk, and then we can do reads or writes from that or to that. So I'm not sure if I'm answering your question, but it means all the file system functionality that you're building is, you have to do all the work. You can't use the fact that there's a file system underneath you. Am I answering your question? Maybe. So do you have a further question? And then, okay, so the other strange thing about this, and I've had numerous people ask me about this, when I'm talking about, like, when a file system, you're talking about pointers in a file system, or what you're really talking about are disk addresses in a file system, those are just going to be offsets into this file, right? That's what a disk address is in this pretend LFS, is you have offsets into this file, which we're pretending is a disk. Yeah?
So it's just like the file is some set size, and then we're going to have different pointers to like the bitmap or the inode map.
Yeah, right. You'll have offsets which point, like there's the checkpoint region, which has like offsets, which are really pointers into that same file, which tell you where the chunks of the inode map are. Those things have, the inode map itself has offsets, which tell you for each inode where it is in the log, or the most recent version is in the log. And then the inodes themselves have offsets in them, which tell you where data blocks are. So yeah, it's just one series of offset referring to another offset, referring to another offset. I'll call those pointers or disk addresses or offsets into this image, but those are all interchangeable here. They're all the same thing, which are just where in this pretend disk image is the thing I'm interested in. So it'll be slightly confusing, but not that bad. And it will make me remember, if I do next time, to make a fake disk layer which only has block read and block write. And then we won't have this problem. So that will be in the future. So not your concern. But you will suffer because of it. Okay, so let us do something up here. Let's look a little bit at XV6 piece here. How many people have played around with this piece? Few of you. Anybody done? Okay, that always makes everybody else feel good at their laziness. Maybe I shouldn't ask that for that reason. Not that you're lazy, more that you're busy, right? You have a lot of things going on, I understand. I was a student once too. It's a long time ago. Yeah. Okay, so here's XV6. We will not do that because we're in the wrong directory. We will build it, and we will look a little bit at some code. How much time do we have? Good, we have a little bit of time. So one of the first things you have to do, and this is talked about a little bit in the last video, but I think not really done, so we'll just go a little bit further, is basically we're changing, logically what we're adding is checksums to a file system, right? So this is based on some of modern file systems do this, that with every pointer or disk address that they store, like in an inode or an indirect block or whatever, they keep a checksum next to it that says, what are the expected contents of that block? Like ZFS is a modern file system that does this. NetApp's Waffle does this. Any file system that really cares about your data being returned to you correctly actually will do this. Amazingly, not all file systems do this, but in some number of years, all of them absolutely will. Because sometimes disks do things like they screw up your data. And of course, they do other things too then. They'll keep many copies so that when you read one and you get bad data, you'll go to the other copy and read that one and hopefully get the right data. Here, we're not doing that piece because it's a bit more work. So all we're doing here is we're just going to try to detect when that a corruption occurred in our disk and then return an error, or in the case, most of the time you'll check and it just works and therefore no error. So what that means is we're changing the on-disk format of the file system. It now has to have not only a pointer but also a checksum. Anytime you change the on-disk format of a file system, it's really painful because it means you'd have to change a tool. What tool would you have to change if you're changing the on-disk format of a file system? What tool do you use to make a file system? Yeah, make file system, right? So if you didn't, by the way, it's an exam question. Hey, what tool do you use to make a file system? Well, how about the make file system tool? Yes, that's correct. You get full credit, but it's called MKFS, and there is one in XV6. Oh, where is it? I don't remember where it is. In tools. That's a good guess too. And you could look at it. And so one thing you could do in this project that we don't have to do, but I'm just telling you for information's sake, is you could say, okay, we're building this new file system, so completely rewrite makefs to make the initial file system like the one we're expected to see. But you know, you look at this code and it's just like, it's a lot of code and it's really ugly and whatever. So we don't want you to have to do that. So the way you know, I define the project then is most of the file system operates in the exact mode that it does today, that most things aren't checked. And only when we create a new file and we specifically pass in an O_checked flag when we create that file, will this new type of checked file be created. And so that makes your life a lot easier. You don't have to change the makefs tool or any of that stuff. You just have to handle the new case when this new type of file is created. Does that make sense? So to do that, then we have to add first thing we got to do is add a flag like that. You can see that in include f control, we have exactly that flag, and we'll add a new one, and we'll call it O_, I think checked. Did anybody do this yet? Checked. All right, very excited. And what, probably 400, something like that. The next bit. These kind of you know, things are used all the time in Unix world. So on O_checked. And then what we're going to try to figure out is, well, where, you know, what we're interested in is where are files created. So let's look at that again. I think we looked at it a little bit last time, but let's look at it again and actually do something with it. So let's look in here. You can see in kernel sys file is one place that this is kind of, well, yeah, that's going to be used all the time in there. So let's go ahead and skip that. Oh, goodness. So let's look for O_create, and you can see here sys open. It says if I'm creating a file, and then what I do is I'm going to make it of type T_file. So this, when I'm opening something and I'm creating it, it's saying call this underlying create routine and make the file of this type, T_file. Now we're adding a new file type, so let's go ahead and figure out where, you know, where that stuff is defined. It's in include stat.h. So let's go ahead and look at that. And what we're doing here is pretty clearly just doing this. We're adding a new, probably t-checked is what I probably called it. And we'll make that, you know, type 4 there. And this is it's a regular file, but it's checked, right? Checked via what? Checksums. So we have to add that, and then what we're going to look at is, you can imagine what we're going to do here. If we're creating a new file, now we have a couple cases. Well, in the normal case, where we basically have where we have a non-checked file, we just do the exact same thing. And when we have a checked file, we're going to do something slightly different, right? So in fact, what we'll do here is we'll check that, and you can see what we're going to do here. If O mode and O checked, right? We're going to do one thing, and otherwise we'll do this thing. This is not necessarily the only way to do it, but you can imagine this is one way to do it, something like this. And so now that we basically go ahead and are saying create a file and call it type checked. Okay? Any questions about that? That makes sense? Kind of straightforward. Now we have to be a little careful. We're adding this new flag, but of course there's going to be places in the code that actually care about t-file. Anywhere that used to care about t-file, these are also, that's just for regular files, right? Typical files. We don't want this code to be any different than that in most cases. So we have to look and see where that is. And you can see actually it's almost nowhere. It's actually just this one other place in sysfile that really cares about t-file, and then in ls, which we could change if we want to, and then makefs, which I already told you, well, we don't need to care about that because that's just creating the original file system. So in sysfile, we should look for t-file and see where this is used, and it turns out to be used here in the create. And you know, you could sit here and figure out exactly what this code does, or you could just say, you know, what do I want to have happen when t_checked gets passed in here instead of t_file? And you can imagine what you want to have happen is basically the same thing, which is returning this basically reference to an inode structure. So let's go ahead and say, well, if it's for a normal file or if it's for a checked file, do this thing. And in that way, what we'll know when we do that is now when we call open with o_create and o_checked, that will, instead of creating a file of type t_file, now we'll be creating a file called t_checked, and basically the code will behave the same for both of them right now, because there's no other place in the code that's checking is this t file or not. The only difference is that now the number 4 t_checked thing is being stored in its inode instead of whatever t file was. Let's say 2. So let's see if this works. Let's see if we can see its results. So let's go ahead and run this thing. Oh no, we have to make a program that uses this first. Let's do that. Okay, so what are we going to do here? User programs, let's call it what? Checksum, check.c, something like that. Let's insert ls.c, that's fine. Let's go down here. Let's get rid of all that stuff. Let's get rid of that. Let's do all that. Okay, so let's go ahead and do this, and then what we'll do is we'll call open, and what we'll pass in, let's create a file, let's call it foo, let's pass in o_create, and let's pass in o_checked. All right, so we're just creating a file. In fact, that's all we'll do right now. Okay, creating a file with o_checked as a flag, and then we have to modify the make file here to make that thing, and let's do that, and then let's build it, and then I didn't do that correctly, and you didn't tell me. What is it, this? Oh, I didn't include the right file, which is F control. Is that right? It is checked. You didn't tell me I was right. I blame you for everything. And then o_create. Oh, it is with an E. You're right. See, now you're telling me. Can't do anything right anymore. See, I'm getting quite old. Unused variable FD. All right, return FD. I don't want to do that. What do I want to do? I'll print it out. There we go. FD %. We just want to know. We're eager to learn what the file descriptor was. All right, good. There we go. So let's see if this crashes. Always fun with live demos. See if anything works. Something's working, kind of. It's booting. All right, that worked. Let's do an ls. That worked. Let's run check. Moment of truth. That worked. Let's do an ls. And we can see foo down here. And actually what we can see is interesting. If you look at what ls is printing out, it's printing out this field is the type of the thing that's being LS'd. You can see dot and dot dot are directories. That's type 1 apparently. These are all regular files. Type 2. This is a special device file. It's the console. And then you can see down here foo we just created. And foo has 4. That's our new type. Okay? So that makes sense, what we did there? Okay, let's delve a little deeper. We have a few minutes, so might as well look. I assume you prefer more rather than less. Right? That's like those, you'd prefer me to do this and that. It's like those bad commercials that are on these days. And is better than or. I'm like, there's lots of cases where or is better. Would you like to lose your right arm or your left arm? Well, I'll take or, not and. Yeah, anyway. Where am I looking? I'm looking in File System, and what we're looking for, eventually what you want to look for is, well, you want to follow the right path. The right path leads to file write, and then that'll eventually lead you into some routines in here, like write I is a kind of an interesting place, and read I. And you can see a couple things I should point out before we go away. You have to look at these loops a little bit because that's where the work is being done. Let's look at the read one. It's a little bit simpler. Read I is being done in here, and read I is calling B read, not bread, right? That's when you know you're a geek, when you look at that and you say, oh, B read. You're like, why is there a sale for B read at the store? That's when you've lost it. I'm sure I make that joke every year, but I still find it funny. So, and then one thing you can see here is an argument that's being passed to bread is called bmap, and bmap is pretty worth looking at because bmap does a bunch of work for you. In particular, what bmap does, if you look at it, and I'm just going to look at the case for direct pointers. For the direct pointer case, it's saying, oh, if the basically what is an inode really doing, right? It's you saying, I want to read block 3 of this file, or really you usually say these bytes of the file, but you can pretend it's this block of the file. What the inode is doing is translating, oh, I want to read this logical block 3 into, oh, this is the disk block that you need to read in order to service that request. And of course it may be many disk blocks because you might be reading a bunch of data at once. So this mapping is kind of this key thing that's being done here. And you can see this code here, what it does is it says, well, if the block you're interested in is less than the number of direct blocks, it means you're interested in one of those first, say, 12 blocks that are directly pointed to by this inode. And the code then does is this very funny little thing. It says, well, if that address is 0, it means that it's not allocated yet. So I'm going to go ahead and allocate a new block and store its address here in IP, the inode addresses in those inodes, those direct pointers at this offset, right? That block number's offset. And then it's going to return that address. In many cases, when you're reading the file, we'll already have this existing, so it won't do this allocation step. What it means is if you can start paying attention to this bmap is you can do things like, you can certainly pull it out here. It returns a uint, I think, something like that. And you can even do things like, print it out, right? So, and this is not a bad thing to do. That we're going ahead and reading some blocks here. And you can do this in the other loop too, and you'll get a sense of what's going on. Now, what you're eventually going to be changing, and we'll do this in a sec if it makes sense, is what you're eventually going to need to change. You're going to need to change what's stored in here, right? You need to change what's stored in that inode, because instead of an address, which is what's normally there, you're going to be storing an address and that little checksum kind of masked or anded onto that or ored onto the top so many bytes. So I'm a little bit out of time there, but you're basically, that's one of the things you're trying to do is change those values, and you're only trying to do it when the IP-type equals t-checked, right? So that's why you're setting that t-checked flag up, so you can basically look in code like this and say, is this one of these checked files? If so, oh, when I'm writing, I need to compute a checksum and store that in there, and then when I'm reading, I need to make sure that I don't try to read from that whole address, that I extract the address, read from the address, then check the checksum, etc. Right? So if you can get that control flow working, you're kind of most of the way towards finishing that part of the project. So I guess I have to stop, and I'll be around for office hours if you're interested in that sort of thing.